Hey everyone, I'm Dylan, and yeah, let's talk about some DNS. So first off, just a quick overview of what DNS is. You might find yourself on a website, and you might ask yourself, how did I get to this website? And there's a lot of answers to that question, but a huge part of it is something called the domain name system, or DNS. And what DNS is it's a series of records about domain names like google.com and their locations on the internet and a bunch of other details that might be useful. So for instance, if we have a client and we want to know where google.com is, we'll go and talk to a resolver. A recursive resolver is one of the two major types of DNS servers on the internet. It's going to be able to answer any question that we've got. And it's going to go talk to authoritative servers that know part of the answer. So the root authority won't know where google.com is necessarily, but it will know who controls .com. And eventually, through a series of requests, we'll get to an authority that actually knows for sure either where google.com is. So in this case, we've got an IP address for google.com, or possibly we'll get a that domain doesn't exist if the authority is 100% certain that the domain does not exist because it controls that realm and there's no such domain inside of it. And this is the high-level overview of DNS. We ask a question, a bunch of authorities get queried, and eventually we get a response. But I was finding myself wondering, like, how does that actually work? What's going on underneath the hood? So I thought I would go read the DNS specification. And it turns out that DNS is actually defined in a series of specs called RFCs, or requests for comments. And these started off as basically memos that computer engineers were just sending to each other in the 60s and 70s, asking for like, hey, here's how I implemented this thing. What do you think? And DNS isn't defined in one of these, or in 20 of these, or in 100 of these. It's actually defined in 266 different RFCs, which is a lot of reading. And it's a lot more reading than I felt like doing. So instead, I decided to approach things like an archaeologist. And when an archaeologist is not taking priceless artifacts and replacing them with carefully weighted grains of rice, or running away from poison darts and into pits full of snakes, what an archaeologist does is ask the question, what is this artifact? What was the culture that created it? What was it used for? And what can we learn about that culture from looking at it? And so if you start looking at the DNS RFCs, you will eventually wind up on this one. This is RFC 1035. It's kind of the main DNS RFC. Almost all of the other ones reference it in some way. And it's a very long document, and it's got a lot of details in it. But it wasn't really meant to be read front to back, though you could do that. It was meant for people who were implementing domain name servers. And so that's what I did. I created a name server and went through the document and tried to build one using it. And this led me to discover a ton of really cool and fascinating things. So for instance, those answers that we saw earlier, this is the packet format for them. So we've got a name like google.com, which is a series of labels. So Google.com, and then the root label, which is just a label of length 0. And then we've got a bunch of other information here. We've got the actual data. So in this case, this would be the IP address. One of the things we've gotten here is this time to live. And this tells us how long we can keep that answer and assume it's still valid before we have to ask the question again. And something I noticed when I was reading through this is that it's a 32-bit signed integer in the resource record. And I was wondering what would happen if it's negative. Like, what does it mean to keep something for a negative amount of time? And then I noticed this red errata exist up in the corner of the RFC. And it turns out that there is an error in the document, and they actually meant to write unsigned. And something that I find kind of fun is that this was discovered in 2010, almost 30 years after this document was originally published. And this is a reminder that these documents are written by humans. Humans make mistakes. Not every design is an intentional design decision. And also, a lot of the design is motivated by the time period and by how people are thinking about things. So DNS grew out of literally just emailing people lists of hosts that were on the internet. Like UCLA would send out an email and say, or probably this was even before email, but would send out a message to a bunch of people and say, like, here's a bunch of servers that we're running, here's their addresses, update your local address books. And DNS was built to be kind of a centralized way of managing all of those addresses. in a time period where the internet looked kind of like this. It was first defined in 1983, and it wasn't even really the internet at this point. And everyone on the internet at this time was an academic institution or a government agency or a large corporation like Bell Labs. You didn't really have commercial and consumer usage of the internet. So they didn't really think about security at all. Like, trust was just kind of assumed in the internet of this day and age. And as a result, we got a bunch of new DNS RFCs that were published in the mid-2000s. To the newest of these was actually published just a year or two ago, to try and add security, because the concerns of today's internet are really different from the concerns of the internet or ARPANET of the 80s. And what I find really interesting is that even these are sometimes outdated now. Like, DNSSEC was developed in 2005. And over the last 15 years, we've seen substantial differences in what we care about when we talk about network security. And it's really easy to look at like something like DNSSEC and say, oh, it's broken or it doesn't make any sense. But it makes a lot more sense if we understand kind of what was going through people's minds at the time and how the culture around security has changed and how they were trying to adapt this existing system that had assumed that trust existed. It's also really cool to see what things people planned for. So because the internet was kind of a new thing, they put this class field into DNS, and they were like, when we develop something better than the internet, we need to have some values to put those in there as well. So this can run on different types of networking protocols that don't necessarily rely on IP and TCP as their backbone. That didn't end up happening. This is a 16-bit field, so there's 65,000 possible values for it, and every DNS record uses this internet value pretty much. We also had the idea that domain names would be case insensitive very early on. So if you type capital google.com into your web browser, it will still go to the same website as if you type it lowercase. But we didn't have a full understanding of character encoding. Unicode wasn't developed until 1988, I believe, or late 87. And so we didn't really know what this meant. Like, there were a lot of code pages and things like that. And so DNS labels were allowed to just contain arbitrary bytes. And the DNS implementers even warned against treating it like it was definitely a valid ASCII code point. So they had to publish something clarifying what case insensitive means if we can't treat something like a valid ASCII code point, because that's kind of confusing. One of my favorite consequences of this is, since any byte is valid, the period character itself is valid inside of a domain name, which the period in google.com is not actually part of the domain name. It's a label separator. So it tells us that Google is underneath com, and that docs, for instance, in docs.google.com is underneath google.com. But we could also just query for a top-level domain whose label name is google.com. And here's Google's recursive resolver, which is 8.8.8.8, telling us that that domain doesn't exist. But what I find kind of funny is Wireshark didn't anticipate this query, so it's not formatted any differently than if it was a correct query for google.com, but we can actually see that what I queried for was the escaped google.com in full, and that's why we get an NX domain there. So yeah, there's like a lot of weird, fun consequences that arise from the things that people wore and weren't thinking about at the time that all of these specifications were developed. And the note that I want to close on is, I think a lot of these things are often frustrating for us as developers. Like, we run into them and we're very confused as to why something would possibly work this way, or what could be going through someone's head to make them design a system that's so obtuse or has all these weird clunky things on it. But all of the tools that we use, all of the technology that we use is developed by humans and developed in contexts. And I think that if we approach a lot of these problems like historians and anthropologists, we can get this, and archaeologists, we can get this idea of why the tool was built this way. And I think it can also give us a lot of information about how to build future tools and how to design them to be more resilient, and the kinds of things that we should be thinking about when we design our tools, and think about how people might use them in the future. So thanks, everyone. Like Alicia said, I'm currently at the Recurse Center. I recommend checking it out if you liked this talk. And also, I know my parents are watching, so I just want to say Happy Mother's Day, Mom, and happy anniversary, Mom and Dad. And thanks, everyone. That was my talk.